So for this lecture, let's take an example on how everything sort of comes together. And what we have here is this triangle which is hinged, H-I-N-G-E-D, at the end. And this is the top view. It measures 2 meter here, it measures 2 meter here, and it weighs 4 kilograms, and you apply a force such that the force is down the plane, and you define this as the y-axis and this as the x-axis. So force is pointing in the plane, like here. You see, this is the top view, but the force is not really perpendicular to the to this triangle. It makes an angle 30 degrees. So your force is sort of, I don't know how to show it, but it makes an angle like this. If we make a three-dimensional figure, then probably it will look like this, so like that. So it's not perpendicular to the surface. So the question is, because of this torque, this whole thing is going to have an angular acceleration about this, and because of angular acceleration, it will gain some angular velocity. So what is the angular velocity after time 4 seconds? So let's begin by calculating the angular acceleration. And we know that torque equals I alpha, and we already have talked about different ingredients. We need to calculate alpha to get the angular velocity, and for that we need to calculate tau and I. First of all, we already know I. We have already calculated that in the previous lecture, which was given as ml square over 2, where L is the length of one of the sides of the triangle, and m is 4, and L square gives another 4 divided by 2. It gives me 8. By the way, what will be the units for I? As you can see, it has kilograms and it has length is square, so these are the units. So this is I. Okay, let's calculate torque now. So torque is given as distance times the perpendicular force that is being applied. Okay, R we already know, it's 2 meters. This is where the force is being applied. But the perpendicular component, this is F, is the component of F in this direction. Now what is this component? Well, you see, if you resolve this using so this is in polar coordinate, you can bring it to the Cartesian system, and I'll suggest to really understand this very well. But if you resolve this, you will see this component is F cos 30 degree, and this component is F sin 30 degrees, right? So you have resolved it, and then F perpendicular is going to be F sin 30, where F is being given, I should have given F, but let's assume it right now to be, F is, let's say, 4 Newton. So F is going to be 4 times sine 30 is 1/2. This is F perpendicular, or if you really want to see, this is actually F sine theta. It's just a multiplication, not a dot product, and that gives us 4. What are the units? It's going to be Newton times meter. You might have seen these units earlier also in case of work, when work was defined as F times D, this force, which is Newton and meter. This is also Newton meter, but work is actually scalar, while torque is vector. And you'll understand why this is vector if you want to talk about something called vector cross product. But let's not do that in this right now. Anyway, so the units for torque is Newton meter. Okay, we have the torque also. We have the torque, so we can calculate alpha to be 4 divided by 8, and that gives us 2 radians per second square. Okay, we have alpha also. Now, how would we calculate angular velocity after time 4 seconds? Okay, no problem. Just invoke the formula which says omega F equals omega I plus alpha Tf minus Ti. We have not been given omega I and Ti, but let's assume them to be 0. Ti is usually 0. We really don't have to worry about the initial time. We can always take it to be 0. But let's say omega is also being given 0. So this turns out to be alpha is half times time is 4 seconds, and that gives us 2 radians per second. So you see how this example integrated all the elements: the torque, the moment of inertia, the angular acceleration, and the equation of kinematics. And most of the equations can be solved using these formulas.